All right, so there are multiple kinematic equations that account for acceleration. If you learn all of them, it can get a bit overwhelming seeing them all at the first time. So we're going to focus on three. I'm going to call them the big three. And I'm going to derive two of them with the velocity versus time graph. And then the third one, just because it is a bit tedious of deriving it, I'm going to just show you guys that one and help you understand why we use it. So you guys can see that I still have our old graphs up here, the position versus time, for if we had constant velocity. And unfortunately, the only time we can really use this graph and do any math is when it is constant velocity. We use the y-intercept formula, but then we realize once we start accelerating, this isn't really of any use to us. We have to focus on the velocity versus time graphs. Well, I put this here because, again, it's y equals mx plus b for the position versus time graph. So our first big three, the first kinematic equation of the big three, is actually going to be doing the y-intercept formula just with the velocity versus time graph. So if you think about it, I have position on my y-axis for this. Now I have velocity on my y-axis for this graph. So it's going to be final velocity equals, we already learned in class that the slope of a velocity versus time graph is change in velocity over change in time, which is the definition of acceleration. So that's my slope. Of course, on the x-axis is still time, so that's kind of nice. That stays the same. And to finish it off, the y-intercept would be velocity again, just the initial velocity, which I'll write as v with the subscript I. All right. Apologize for the shaking when I put my hand on here. It's not as sturdy as I would hope. All right, but this is actually going to be our first of the big three equations. All right, you can see it definitely accounts for acceleration, and it also kind of makes sense that there's acceleration because there's a final velocity and there's initial. Whereas this one just had one velocity, which kind of implies that the velocity doesn't change. So that's a major difference, okay? So we can, if you want to, we can just label this 1. What you probably recall is this could be rearranged to basically be the slope formula, which is rise over run, all right, our displacement over our change in time. You could technically do the same with this. You could rearrange it, and it would basically be the change in velocity as the rise over the change in time, the run, which is slope, and that's acceleration again, okay? So it's another variation of that slope formula. All right, the other one that we haven't talked about is not slope. So that's mainly why I'm doing this video, to save some time. The other one that we're going to do is something else you can do with graphs besides slope. And the other thing that you can do with the graphs is you can actually find what we call the area under the curve. So if you basically, from where the data is, create a shape beneath it down to the x-axis, this is now creating a triangle, and it has an area which we say is underneath the curve of the data. All right. We can actually calculate this area quite easily because since it's a linear fit for the acceleration here, our slope, it's just a triangle, which is 1/2 base times height. All right. If you think about it though, the base, so let me put my 1/2 there, the base is a measurement of time. And the height is basically a change in velocity, all right? Or you could even just say, I guess, a velocity right now if you just want to kind of shortcut it, all right? The question then is, what the heck is this equal to? Like, what is a velocity multiplied by a time? Forget the 1/2, who cares about that? Well, this won't be too hard to figure out because if we actually think of our old equation up here, we did this earlier where we moved the initial position to the other side by subtracting, and we knew that final position minus initial is what we call displacement. The only thing that was left on the right side then was a velocity multiplied by time. So this is what's pretty cool. Anytime you have a velocity multiplied by a time and that's all there is, that is always going to solve for the displacement. So don't worry about the 1/2. We have a velocity multiplied by a time, so this must solve for the displacement the object traveled. So this is kind of a cool idea. A velocity versus time graph can of course tell us the object's velocity by just looking on the y-axis. It can also tell us the object's acceleration by calculating the slope, but it can also actually solve for just total displacement, not specifics, of positions, but just total displacement by doing area under the curve. Okay? Unfortunately, though, I'm not going to just leave it at this. This isn't really the second equation because this would only help us if the initial velocity was 0, which is not always going to be the case. So what I'm going to do is I'm going to redraw this with a scenario where the initial velocity is not 0. So what if it starts somewhere up here? Let's call this initial velocity. All right, still going to be a linear fit and still going to be accelerating. Let's call this guy up here final velocity. All right, the issue now is that this actually doesn't make a nice triangle. If we do area under the curve, it creates this funky shape. Well, the general rule is we always want to break it down into simple shapes. So if I do break it down right there, I actually still see my triangle portion, which is pretty nice. That's still the 1/2 times t, but we're going to mess with that v part a little bit, okay? Because that's got to be the height. The other thing is the bottom is a really nice shape. It's just a rectangle. Okay, so I'm going to do this idea again of trying to find this total area, but I'm going to do it for each shape and add it up. Good news is we know that it's already going to equal the displacement. So why don't I just say, hey, these areas, it's definitely telling me a displacement. All right, so let's do this. Let's start with the easy one. Let's start with the rectangle on the bottom. Base times height, I'm going to go out of order. I'm going to go height first. All right, the height is basically from 0 to vi. So if I subtract those two, it's really just a height of the initial velocity. The base would then be whatever time has passed. All right, I don't know if you guys see something interesting. If you don't, I'll get to it, but a light bulb might have turned on for some of you. The triangle is going to be, again, base times height, but 1/2, since it is a triangle, of course. So I've got my plus 1/2. I'm going to do the height first, just because I think it'll be a nicer organization. But the height, this right here, is actually the final velocity minus the initial velocity. Okay, so I'm going to put this in parentheses. I've got final velocity minus initial velocity. And then the base is still just a time. All right. This technically right here is the foolproof second equation of the big three. The problem is, though, I don't see explicitly, I don't see acceleration in it anywhere. Okay, so I'm going to show you guys a little trick. If I basically took this equation right here, which I'll try to do it to the side so you don't get confused. If I basically subtracted vi to the other side, I would then have vf minus vi. So this expression equals, I'm even going to put it in parentheses, why not? Equals a times t. Well, if you look at the equation we just created, we have an expression of vf minus vi. So I'm going to, instead of leaving that as vf minus vi, I'm going to replace it with what it's equal to with this equation, a times t. So then it's going to say the displacement equals the initial velocity times time. And I'm going to spoil it now. I don't know if you guys noticed it, but this is basically our representation of displacement when it's a constant velocity. So it's filling out that first part if it doesn't start from rest and has an initial velocity. All right. But what if it is accelerating? That's where this second part, the triangle, comes into play, where you can see the velocity changing, of course. It would then be 1/2 times, I'm going to replace vf minus vi with a times t, and then I still have to multiply it by the time. All right. I'm going to clean this up just a tad right here. I see two like variables in this multiplication, so the final expression is going to say displacement equals vi times t, which accounts for the rectangle, which would be constant velocity if it were just that. and then plus the displacement it'll have from changing its velocity during the acceleration, which is the triangle, 1/2 times a, and I'm going to write that instead as t squared. So this big guy right here, it's a bit intimidating, I'm with you on that, but this big guy, this is our second of the big three. All right, and this came from basically not the slope of the graph, but the area under the curve, which represents displacement of the object. Okay, so we've got the first big of the three, which that was pretty easy to understand. That was, of course, the slope. We talked about that. The second, which was a new idea, area under the curve, and even the area if it doesn't start from 0, which makes it a bit more tricky. And then the third, which I'm not going to derive because it's using another equation we haven't talked about, and I think it would just kind of have you lose the big idea. The third is a combination of this equation and another. It is VF squared equals VI squared plus 2 times A times delta X. Why am I showing you this third one and like it just came out of thin air? Well, you'll like these three, at least out of all of the equations. I think you'll like them the most because this is a good one to use if you don't know the displacement of the object. All right, because there's no displacement in it. So if you know these four, or are solving for one, of course, this is a great one. This one right here is a good equation to use if you don't know the final velocity. All right, of course, we're not trying to solve for the final velocity. We just don't know it and don't really need it. This one right here is a great one to use for, you guessed it, the time. If you don't have the time, my apologies. If you don't have the time and don't need the time, this is probably what I would use. All right, so let's just kind of highlight these. I'll refer to them as equation 1 or maybe the VF equation. This one would be, of course, equation 2 or the displacement equation. And again, the cool thing that happens with this, what if it's not accelerating? Well, look at what happens. 1/2 times 0 times t squared, whether we know it or not, drops off. And hey, surprise, surprise, we're actually back to our constant velocity formula because the acceleration was 0, so that disappears. So that's why this is a big one, because it'll account for if it is accelerating, or if it's not, it'll take us back to the original. All right, and our third equation, which was the mystery appeared out of nowhere because Mr. Bank didn't want to confuse you, we'll call this the third or the VF squared equation, all right? All right, this is why those KU charts are so important, because when you get a word problem, the question is then going to be, what equation do I use? The KU charts are going to help you figure out what you know and what you're trying to find, and that will then set you up for choosing the appropriate equation, all right? Also, even though these came from graphs, when we do word problems, you don't need to try to create a graph, all right? When we do strictly word problems with math, the whole point of having these equations is to be able to just solve them with the equations, all right? So even though you're getting pretty good with graphs because we're using them a lot, word problems, you don't need to go back and draw these graphs, all right? If you want to, because you're just so geeked out about physics, go for it, but it's just for the equations to help us shortcut with the math, okay? All right, I hope this helped, guys. Refer to it whenever you need a reminder, okay?